So, graphs can contain various types of information about the type of motion that an object is undergoing. When doing calculations with graphing questions, consider three important components: the axes, the slope. Recall, you always need 2 points to calculate your slope. Slope is equal to rise over run, which is equal to delta y over delta x, which we say is y2 minus y1 over x2 minus x1. We also need to look at the area under a graph. So the area under the graph is always in reference to the x-axis. You may need to break the area under the graph into 2 or more shapes. So if it's an irregular shape, you might have a triangle plus a rectangle plus another triangle. So these will give you, the area will give you different things depending on what your axes are. So when you find the area, we'll just give you the different formulas. So an area of a triangle, anyone remember? Length times width divided by 2. Squares and rectangles are both just length times width. So when we're looking at these graphs, uniform motion, which means constant speed. So this is like constant speed or velocity. This is when you're setting it to cruise. Okay, you're on cruise control. You're not accelerating, you're not slowing down, you're just on cruise. Okay, that's what uniform motion means. So let's look, say, at a distance versus time graph. So let's put distance on the side. Distance in meters. This could also say position, okay? And we have time, and let's say it's in seconds, just using kind of our standard, what we go for. This axis is positive, and this is going down. As I go up, it's positive, going down, it's negative. All right, and I have my 0 here. So I'm just going to give you an example of what a distance-time graph might look like, and then we're going to analyze the different parts of it. So let's say it goes up a little ways, it plateaus, and then goes down. Actually, when it goes down, make it go down steeper than how it was going up. So let's think about what this means. In reference, when I look at these two slopes, which one is faster? The steeper one or the not steep one? Steeper one will be faster. So this is a faster speed than what I started with. This here, at the beginning, this is a slow speed. What's happening here in the middle? Nothing? At rest. So when it's plateaued, when it's just plain like that, it's at rest. Okay. Now, if I have my distance, say I'm running, this is me running, and I'm running at a slow speed, okay? And then I stop for a rest, what does it mean that I'm going down? Does that mean I'm going down a hill? What does it mean? I turned around. Yeah, so that's a change in direction. So this spot right here that means a change in direction. It's my change in direction.
Starting point.
Pardon, sorry?
Like, do you ever tell your starting point or your end point?
For what?
Changing direction. Or at rest.
Like in a calculation, you mean?
Like, yeah, could you assume there's at rest when you start?
Yeah,
You know?
yeah. Like right here? Is it at rest?
Yeah. But
I would make the assumption that, yeah, at that axis, yeah, you would be at rest.
so is that like a direction change or it goes from being at rest to?
No. It's just, nothing's happening, and then you go. Yeah. Okay, so slope, then, we know, is rise over run, equal to delta y over delta x. So, what is my y-axis? What's it called? It's distance, so I can say this is the change in distance. And my x-axis is time, so that's my change in time. What is d divided by v? That's really velocity, right? Therefore, when you find the slope of a distance-time graph, it equals velocity or speed, depending on if you're asked to give direction or not. Okay, so now let's do velocity versus time. So let's put velocity on the side. And we'll have our time is still our x-axis. Velocity, the units we need to make sure we put in is meters per second. Again, going up, positive, going down, negative. Okay, so again, let's look at an example. We're still doing uniform velocity, so we just see it going just straight across. And just draw a dotted line down. And then leave a bit of space, draw a dot, and then there's a line down here. You can draw dotted line, just the dotted lines represent how we find area. But this is the actual plot, okay, these two lines. So, here, this is my area 1, this is my area 2. Area 1, area 2. What's happening right here? If I'm at 0 for velocity, what am I doing? I'm standing, I'm at rest. Not moving, okay, during this time. So that's this point right here. Object at rest when graph is on the x-axis. Meaning when your velocity is 0, you're at rest. You're not moving anywhere. Okay? Object changes direction when the graph crosses the x-axis, either positive or negative. So this is a change in direction. Okay, I change direction. Okay. Oh, we didn't do area. So area equals length times width, which really, if we were going length times width, that's V times T. What is V times T? Distance. Okay. But wait, I want to say one more thing. If it's actually velocity, what should I have over this V? An arrow. And what should I have over this D? An arrow, because if it's actually velocity and not just speed, it's velocity and displacement. Okay, let's have a break.